This lesson is about similar polygons, and the objective is to identify and apply similar polygons. So the first definition is similar polygons. Similar polygons, you could also call them similar figures, have the same shape but not necessarily the same size. You can abbreviate the phrase "is similar to" with this symbol. It's a squiggly line, it's a tilde on your keyboard. Two polygons are similar polygons if corresponding angles are congruent and if the length of corresponding sides are proportional. So let's look at this figure below. So here in this figure, if we identify the corresponding angles between quadrilateral ABCD being similar to quadrilateral GHIJ. Once again, you can go by the names like you do with congruence to indicate the corresponding angles that go together. So here we're going to have angle A is congruent to angle G, angle B is congruent to angle H, angle C is congruent to angle I, and angle D is congruent to angle J. And then the other relationship we have here, the corresponding sides are not congruent, but the corresponding sides are proportional. So that means if we put side AB over side GH, which is its corresponding side, make a ratio out of it, put an equal sign so we can make an extended proportion out of this. And then we can go on across with the other corresponding sides. BC, so that's going to be equal to BC over HI, which is going to be equal to CD over IJ, which is equal to AD over GJ. So those are the corresponding sides that are going to form an equal proportion. So we can write a similarity statement with corresponding vertices in order, just as you write a congruent statement. And we'll write an extended proportion when we have three or more ratios that are equal. And instead of writing that again, this is the extended proportion here. Where in this example we had a quadrilateral, so we had four ratios that were equal to each other to form the extended proportion. The last definition we have is going to be for a scale factor. A scale factor is the ratio of corresponding linear measurements. In this case, with a polygon, is linear measurements of the sides of two figures. So let's draw an example here. Draw a right triangle that's ABC with lengths 15, 20, and 25. And then let's draw a smaller right triangle with lengths 6, 8, and 10. We'll label that one triangle XYZ. So here we have a similarity statement. We can write triangle ABC is similar to triangle XYZ. So we're given that information. So to find the scale factor between these two triangles, you're going to take the lengths of corresponding sides. So for instance, BC corresponds to YZ. Once again, if you're not sure which sides go together, you can always tell by the name, okay? BC goes with YZ in the name. Then put the sides that correspond to the lengths, 20 over 8. Reduce that. 4 will go into each of those. 5 over 2. So that is your scale factor between these two triangles. And you could also write that as a different format of the ratio, 5 to 2. So let's look at some problems that use proportional sides and the extended proportions and scale factors. In problem 1, it indicates that triangle QRS is similar to triangle DEF. So the first question is, what are the pair of congruent angles? You can go by corresponding positions in the name to get that. Angle Q is going to be congruent to angle D. Angle R is congruent to angle E. And then angle S is going to be congruent to angle F. Those are the corresponding angles that are congruent. Now, what is the extended proportion for the ratios of the corresponding side lengths? Since it is a triangle, you're going to have 3 sides. So find your corresponding sides and make it into a ratio. So QR corresponds to DE, and that's going to equal RS, which corresponds to EF, and that will be equal to QS, which corresponds to DF. Corresponding sides between those two triangles. Now let's look at problem 2. In problem 2, you're asked, are the polygons similar? And if they are, write a similarity statement and give the scale factor. So here are the two triangles. We have an A or ABC and FED. So the question is, are they similar? So to do this, you're going to have to compare the lengths of the sides and see if they are equal ratios. So let's look at the comparable sides. The sides that go together, that correlate together, are AB goes with FE. And we want to know, is that equal to BC over ED, which is another pair of corresponding sides, and is that equal to AC over FD, or your other two corresponding sides? So now substitute in your numbers. AB is 15, FE is 30, and that is going to be equal to BC is 17, ED is 34, and AC is 8, and FD is 16. So those are, if you reduce that down, 1/2 is equal to 1/2 is equal to 1/2. So yes, we can write our similarity statement. Triangle ABC is similar to triangle FED. On the next problem, we have two quadrilaterals, LMNO and QRST. So once again, look at your corresponding sides. LM corresponds to QR. We want to know, is that equal to MN over RS, which we want to see if it's equal to NO over ST, and is that equal to the last side, LO over QT? So now let's substitute some values in. We have 4. LM, the length is 4. QR is 6. We want to know, is that equal to MN is 10 and RS is 16. We can go ahead and see at that point, if I reduce this down, that 2/3 is not going to be equal to 5/8. So we don't have to go any further. These are not similar, so we don't have to look at the rest of the ratio. Let's go to problem 3. Problem 3, using similar polygons. You have two quadrilaterals again. WXYZ is similar to RSTZ, and it asks what's the value of X. So since you know that they're similar because of the similarity statement, you can look at the corresponding sides and set them up with a proportion. So in this, we can put WX corresponds to RS in the inside quadrilateral, and then that has to be equal to the other side on the larger quadrilateral is XY, and that one corresponds to side ST on the smaller one on the inside. So now we can substitute the values. WX is 24, RS is 16, 20 is the length of XY, and then ST is X. So here we can use the cross products property and multiply your 24 times X is equal to the 16 times the 20, which is 320. Divide both sides by 24, and X is equal to 13.33, repeating, which is B, 13 1/3. In the last problem, it says Jan uses an overhead projector to enlarge a picture that's 5 inches high and 7 inches wide. So let's draw a rectangle that is 5 inches high and 7 inches wide. She projects the picture on a blackboard that is 5 foot 2 inches high and 12 foot wide. Once again, we need to convert this so that we're comparing the same measurement. So 4 foot 2 inches high, 4 feet times 12 is 48 inches. So 48 plus 2 is 50. 50 inches is the 4 foot 2 inch side. And then 12 feet wide, 12 times 12 is 144 inches wide. So now we can compare this. So we need to compare both of the heights and both of the widths to see which one we would run out of first if we tried to fill it with 5, if we wanted to fill that blackboard with that 5 inches high and 7 inches wide. So let's look at how many times. Let's compare the 50 and the 5. So 5 will go into 50 10 times. And compare the 144 and the 7, and that's 20.6. So we would run out of the height first. That's what we would fill first, is the height. So we can enlarge it at most. The most we can enlarge it is 10 times. So that gives us the 5 by 7 enlarged 10 times. So we have got 5 inches. We have the 5 by 5 by 7, and we need to multiply that times 10. So that's going to give us 50 inches by 70 inches, or converting it back to feet and inches, that's going to be the 4 foot 2 inches by 5 foot 10 inches, if we convert that back to feet and inches. So that's going to be the dimension of the largest picture that can be projected on the blackboard, are these dimensions.